Hello again. This is the second part of our presentation on dosers. We'll be covering the doser production estimation. Of course, as you know, the doser has no bowl or hopper or tank in it, so it doesn't have an exact fixed capacity that you could note. However, you could estimate the capacity either from field measurements or whatever, there are different methods to estimate the capacity. However, the capacity is not the only thing to govern the production rate. You have other things. I mean, you need also to know the type and condition of the material, the circumstances of the job, and the cycle time. So, in order to calculate the or estimate the productivity, you have one of three options: either to use the manufacturer rating, or you have previous experience. So manufacturer rating, that means you have some catalogs or tables or whatever, and we'll be discussing this issue. Or you have previous experience, somebody used this thing before, or you have used it before, and you know that this is the productivity. Or you will have some field measurements to be done in order to calculate this production. So those are capacity estimation. There are four different approaches. We'll be only covering the first two because the other two, they are not within our scope. So standard approach, simply speaking, you're assuming that you have a width L and a height H of the soil in front opposite to the blade, and you're assuming a slope of 2 to 1 of the soil that you are pushing. Based on this assumption, the capacity is H times 2H times L over 2, which is H squared L. This is with side slots, which means that this is if you are not allowing the soil to drop from the sides. So this is mainly if you are using a U blade. However, if you are using an S blade, the sides, the two sides, you will find soil to be lost from the sides. So in such a case, you are assuming a loss of 25%. So the capacity is 0.75 H squared L. Church approach is very similar. However, the difference here is the assumption of the height and the slope. So here it's 1.1 to 1.6, the ratio between the height and the horizontal distance up in front of the blade. So in such a case, if you do the calculation, you will find it the capacity to be 0.79 S squared L if you are including your sine slots, if they are confined, if you are having a U blade. However, in case of an S blade without side slots, you will be losing a portion of this number, so you'll have 0.59 H squared L. So those are production models. We have four different models. However, the two within our scope are the general output model and the Caterpillar production curves and correction tables. And they are named after Caterpillar because that company was the first one to develop that technique of having curves and tables to use them in order to get the productivity. We're not doing any advertisement for them or something like that, but it is based on their rights in terms of they have been developing this thing for the before other companies, and then other companies walked on their steps. So the general output model, it's based on a very basic concept that you have the capacity in the numerator. This is Q. You have some correction factors F, K, F2, and small t, and all these are correction factors in the numerator too. However, in the denominator, you have the cycle time. The cycle time is categorized into fixed cycle time, which is T node. This is for loading, turning, dumping, and raising, lowering the bucket. Or sorry, this is the type, it's a blade. And a variable cycle time, which is d over v1 plus d over v2, which is v1 and v2 are the holding and returning speeds respectively. The coefficients that we'll be discussing, the factors, F is the earth volume change conversion factor. So all of these equipment you are producing us productivities in terms of loose units. So now you need to convert from loose So the capacity, the blade capacity is in loose cubic yards or meter cube. So you need to convert it from loose to banked, because when you are doing field measurements to measure exactly what the amount of soil that has been excavated, you're doing it based on banked units. So in order to deal with contractors properly, you need to have it in banked units, and also because unit prices typically are given per bank cubic yard or per bank cubic meter. So you need to change the earth volume, and of course there are job and management conditions, the F2 factor. There are operating time factors, the efficiency, which is 50 over 60 or 45 over 60, the number of minutes per hour. So depending on your previous experience with your labor or with your drivers or with your crew working on site, you will be determining what is this number in specific. And then the K is the blade capacity correction factor, and we will be discussing it in detail. So this is the dozer fixed cycle time, depending on the power, whether it's power shift transmission, direct drive transmission, or you are having hard. The K factor is very interesting in terms of changing. So the capacity that you have calculated for the dozer is based on a leveled grade, a grade of 0. So if you are having a grade of 0, this K will be equal to 1. However, if you are digging downhill, if the grade is negative, you will find a factor that's more than 1. If you are digging uphill, your factor is higher than 1. Why is that? Because the capacity is less uphill than downhill. The capacity is less, so the productivity is less when it's uphill, while it's more when it's downhill. That takes us to the caterpillar model. The caterpillar model makes life easier now. Now you don't need to go and estimate the capacity and estimate the cycle time and do this division and multiply by the factors. It saved you the calculation step for the ideal production. However, it gave you something else. It gave you an ideal production in the y-axis, versus in the horizontal axis it's the average dosing distance, or what this is what we calculated before, what we called the average hauling distance. So this average dosing distance for different models of dozers have different curves. Of course, the larger is the dozer, the higher is the curve, the higher is the productivity. Okay, the larger is the dozer in size, the higher is the productivity, and of course the more is the cost of owning such a dozer, or the cost of renting such a dozer. Okay, so if you look at the average dosing distances, by the way, here we are talking about all of these dozers are denoted by S, A24S, A34S, D7G7S, D7H7S, so on. So these are all S blades. They are all straight blades. So if you look here, the range for the average dosing distance starts maybe from 90. This is the absolute maximum for maybe for the if we look at D7 S, number D or number C, you will notice that the maximum here is 400 feet or 120 meters. However, if we look at D7H7U in that slide for U dozers, we'll find that the maximum distance has significantly increased. It became 135 meters instead of 120, and the production has significantly increased. And again, this production is ideal production in terms of loose meter cube per hour or loose cubic yards per hour. So this curve is showing us that the D7 the 7U is higher than the 7S, or 8U is higher than 8S. Each U blade, even when using attached to the same dozer, it will give us a better production than the S counterpart, and it could cover a larger average dosing distance. Um, Here we are having some assumptions for ideal production. So we're assuming a 60 minute per hour, 100% efficiency, a power shift transmission machine with 0.05 minimum minute fixed time. The machine cuts for 50 feet, then drifts the blade. The soil density is 2,300 pound per LCY. The coefficient of traction in terms of track, for a track machine is zero point 0.5 or better. The wheel, in case of a wheel machine, is zero point 0.4 or better. The use of a hydraulic control blades. So if these assumptions changed, you have to adapt for these changes. But how could we adjust for soil density, for example? Simply speaking, if you are using a heavier soil, you should reduce the production down by the ratio between that weight of the heavier soil and the 2,300 pound per LCY. If you are having a lighter soil, you will multiply by 2,300 over the unit weight of the lighter soil. So this is simply how you adjust things here. So again, we get the ideal production from the curve and multiply it by the correction factor that we will. Of course, this K-blade correction factor that we have discussed previously applies here too. Here you are having different correction factors depending on the different factors, whether the operator level of skill, the material type, the technique of dosing, whether it's slot dosing. Slot dosing is a single dosing, side by side dosing, visibility, or sorry, slot dosing. A single dosing is one. It's if there's one doser doing the job, it's one. Slot dosing we mean here by having an overlap between two tractors working beside each other. Side by side is that they are exactly beside each other. Visibility. Visibility, you have dust, rain, snow, fog, or darkness, you will reduce it. Job efficiency. Direct drive transmission, it's 0.1 minute fixed time. In terms of correction for traction, if you need to correct for traction, so if the lower value of the coefficient of traction is 0.4, then you need to decrease the production by 4% for every 0.01 in the coefficient of traction below 0.4. So for example, if the coefficient of traction is 0.35, you will need to reduce it by 20%, which is 0.05 times 4. So let's take an example. A bulldozer excavating common earth. The earth volume change conversion from loose to bank is 0.8. The hauling distance 45 minutes, and it's leveled. The side plates measure 1.53 by 4.23. The blade is equipped with side plates and it measures 1.53 by 4.23. The doze's average forward speed is expected to be 40 meter per minute, whereas the turn speed is 53.3 meter per minute. The fixed cycle time is 3 seconds for shifting gear for 2 gears, and total fixed cycle time is 6 seconds per cycle. The hourly cost of owning and operating the dozer is $23.56 per hour. The job and management efficiency factor is estimated to be 80%. Average operating time can be 50 minutes. So you first calculate the capacity. So 1.53 squared times 4.23, this is 9.9 meter cube. The cycle time, this is the 6 seconds, plus 45 over 40, plus 45 over 53.3, this is a typo here, it's not a 1. So this is 2.06 minutes. Then you get your factors. K is 1 because there is no grade. So 60 times 9.9 times 0.8 times 1 times 0.8 times 0.83 times 2 over 2.06. The 0.83, this is the efficiency. The 0.8, one of them is for the unit conversion and the other is for the F2 factor. Then we get 153.73 meter cube per back meter cube per hour. Then the unit cost is the hourly cost divided by the productivity, so this will give us $0.153 per bank meter cube. That's it, and thank you.